The inclined plane. Hello there, peeps. Hang with me. This is going to be kind of a challenging lesson in that it includes lots of elements, lots of geometry in order to analyze a situation like this. Let me show you the situation here. We have an object and it's on what's called an inclined plane, basically a slope or a hill. And here's the horizontal and here's some angle, theta, where this object is going to, intuitively we know it's going to accelerate downwards. It's going to fall, but on this plane. It's falling at an angle instead of straight down. So, what does that mean? Well, we know that an object that falls straight downwards on the surface of the Earth will accelerate 9.8 meters per second squared. And because this is falling at an angle, not directly straight down, it's going to be some fraction of that. And that's what we're going to do. We're going to find out by analyzing the geometry here what that fraction is. How do we find it? So here's the basic gist. We know that in this case over here, we've got the force of gravity, mg, acting on that mass, okay? So gravity wants to bring it down in this direction. Well, we know though that the motion is going to be in this direction over here. That's where the A is pointing. And therefore, some fraction of that force will be pointing in that direction. We'll determine what that is at some moment. We also know that this object is pushing down on this surface. Even though the surface isn't horizontal, it's on the incline. And therefore, if this thing is resting on the surface, that surface will be pushing up on it. And we're going to have a normal force as well. So we must have this normal force because it's got to be pushing up on it. We got to figure out what that value is as well. So this is force normal over here, like that. All right. So what we're going to try to find actually is, well, if something's pushing down, how much of it is doing that? So we have this thing here. There must be a force pushing down because of the gravity in this direction. Part of the gravity is going to be pushing down. Part of it is going to be accelerating this object in this direction. So I'm going to model this over here. But this is the first time we're going to do something called rotate our coordinate system. What we'd like to do is set the x-axis to be in the direction of the acceleration, which is parallel with this plane over here. So check this out. We can totally do this. This is well within the rules. We can rotate our coordinate system so that this is positive x over here, and this is positive y up here. So what's kind of interesting is that this acceleration will be in the direction of our positive x, and the normal force will be in the direction of positive y, and the rest of the stuff we'll kind of figure out as we go along. So we're kind of missing something over here. We want to know one of these key angles. Since this side is definitely a player, this is the amount that gravity is pushing down on the surface, and the surface is responding in kind due to Newton's third law of motion. We want to figure out what this angle is over here. Well, I'll put a big question mark there, actually. Let's try that question mark. Hey, what is that angle? To do the analysis takes a little bit of geometry, so I'll use the space over here and hang with me. All right, so what we got is this triangle from before, like this, and we've got the angle theta there. Excellent. Notice that this side over here, okay, I'm going to extend that parallel down here. So I'm going to make this rectangle, essentially. Here we go. And that this line and this line, they are parallel to each other. Okay. I'm going to use another color. And I'm going to complete this box, this rectangle, by adding these sides over here. And the angle of interest is this one right here. Okay, so we have this angle from before. This is our horizontal. This is our inclined plane. That's the angle theta over here. And I've boxed this in to kind of help me draw other triangles to figure out if we can understand what this one is right here. All right, well, by doing that, I noticed that this thing was a right triangle because that's what it is. That side is a right triangle here, or this triangle is a right triangle. These two are the adjacent and opposite sides, and so that's the situation over here. And so I know that in any triangle, the sum of these angles has to be, well, if you want to use degrees, 180 degrees. Here's 90, here's theta, and so this must be something like 90 minus theta over here, okay? Interesting thing though, if I'm interested in this angle, the one with the question mark, then I notice that where these are supplementary angles, these are complementary angles next to each other, because that is a right angle over here. This is 90 degrees. So I have 90 minus theta. In order for that to equal 90 degrees, then the question mark has to be, guess what, theta. So this angle here is actually theta. So I'm going to replace this question mark, and it's really convenient to use because now if I know the angle of the horizontal and the inclined plane, I also know this angle over here, and it's going to help me break down gravity's effect on this box accordingly. So now I have, believe it or not, another right triangle that I can use that represents the amount by which gravity is going to be pushing down on the surface and the amount by which it's going to be accelerating this object. So here we go. If this is the angle, this is the opposite side, and that opposite side is going to be the hypotenuse times the sine of the angle. So this is mg times the sine of theta, okay? This is how much the acceleration will be, some fraction of acceleration, g sine theta. So it's related to the to this angle. So if theta is 90 degrees, then I get full g, because then it's straight up and down. And if I get 0 degrees, sine of 0 is 0, and I get no acceleration. So that totally makes sense in terms of the trigonometry. How about that other side? Well, the other side that's actually pushing down on the surface over here, thanks to gravity, is the component mg cosine theta. This is the adjacent side. And because mg cosine theta is pushing down on the surface is pushing back on it. And so we get force normal that way. So depending on the angle, now the steepness depends on how much acceleration we get and how much normal force we get as well. So I could actually throw in another force over here because we've worked with friction. I can call this the force of friction, which has a relationship to force normal, as we know, based on the coefficient of friction. Okay, so with our rotated coordinate system, we now have an ability to analyze what's going on here because of the fact that the positive x direction is now, we have a component mg sine theta, friction is in the negative x direction, the normal force is in the positive y direction, kind of like it's always been, and the difference now is that the amount of weight on the surface is related to the cosine of that angle. So let's look at the next piece. How do we write those equations for Newton's second law? Well, here we are. And so what about Newton's second law in the inclined plane? Well, now I've drawn the situation we had before in a similar manner. Technically, I should probably have an mg down here because that's an actual force. But what we see in red is that, of course, the force of gravity breaks up into its components relative to this coordinate system. So I have downward, I have the mg sine of theta, that's the amount that's going to be pushing it down the hill. I've got mg cosine theta pushing on the surface, responded by the normal force, and I've got friction competing against it, which I've written down here as mu force normal, thanks to our rotated coordinate system. So how does this work if we're going to write the equations down based on this free body diagram? How does Newton's second law work in this? Okay, sum of the forces in the y direction equals mass times the acceleration in the y direction. So the thing is, this is 0, and why is that? Well, if we look over here in the y direction, it's not accelerating in that direction. We have a normal force, which automatically implies that it's not going to be accelerating in that direction. The only acceleration is down the slope. So it's not going to be moving along this y direction, just the x direction, okay? That's part of the reason for the simplified, for rotating the quarter system. It actually simplifies things. It sounds complex, but it makes things much, much easier. So let's write down what we have. In the positive direction, we've got force normal. All right, so we got force normal minus mg cosine theta. All from the diagram. This is why we make the diagrams and why it's an absolute requirement. And that equals 0, thanks to the acceleration in the y direction equals 0. All right, so what does that say? It says that the force normal is equal to mg cosine theta. Right on. All right, how about the x direction, where all the action is, where we got the acceleration? That's the motion. Okay, this mass will accelerate because of this net force in the x direction. Well, I've got in the positive direction, going down the slope, mg sine of theta. I'm going to just do that in different colors so it sticks out. Mg sine of theta minus mu force normal. Well, I'm going to make a substitution on the fly if you won't mind. I know that force normal from the y direction is mg cosine theta. So I'm just going to throw that up here and say that, okay, the negative force, the friction, is going to be mu times force normal, which is mg cosine theta. All right, and that equals max. So if I want to figure out what ax is, I realize that it's not a function of the mass at all. Look at this. Every term has a what in it? Okay? Just like any falling object that we've seen, it's not a function of its mass. A heavier object does not fall faster than a lighter object, barring the air resistance and other factors, right? So, but by itself in a vacuum, all these guys would move at the same accelerations. That's also the case for a downward slope. It would have to be the case, even with friction. Okay? But there is something, mu is a term in here, but not the mass. All right? So the acceleration is just equal to the g sine theta minus mu g cosine theta. And we could factor out a g because that would be a cool thing to do. So let's do that. So the acceleration ax is equal to g times the sine of theta minus mu times the cosine of theta, like that. All right, so this is our final result. This is our final expression for the acceleration down the slope with friction. It's some fraction that's based on the trigonometry, or you can call it geometry, g times the sine theta minus mu cosine of theta. So that's the basic case here. So we'll try an example with numbers coming up and see how well we fare. Smartly done. More ad. Out.